In this video, I'm going to talk about the ET data type, which is built into the Zen language. The ET data type just stores intervals or notes of equal temperament. To create a value of type ET, we just type the number of steps and then the number of equal divisions of the octave, in this case 12. So this is 4 steps in 12-tone equal temperament. We can get, so that's like basically a major third in 12-tone equal temperament, and this is a major third in 19-tone equal temperament, which is 6 steps. Because it's so common to create 12-tone equal temperament notes or intervals, there's a shorthand which is just putting a pound sign and then the number of steps. So this evaluates to 4 steps in 12-tone equal temperament. Another way to create these is to use a function which is ET, and it's very similar to the operator, this little hash operator, except you pass the number of steps as the first argument and then the number of divisions of the octave as the second argument. So these two statements are identical to the first ones we made. And similarly, if you just want to create a 12-tone equal temperament interval, you just type in one number. So a question I've been asked is, we can create equal divisions of the octave, but what about equal divisions of other intervals? For example, there's the Bowen-Pierce scale, which is a 3-to-1 ratio, that's like an octave and a fifth, divided equally into 13 parts. So the way to create something like that is to use this ET function. If I wanted one step in this Bowen-Pierce scale, I just say I want one step with 13 equal divisions, and then the third argument here is the size of the octave. And it's a kind of a pseudo-octave actually, because it's not equal to 2-to-1. So now I get one step in an equal temperament, which is technically 8.2 steps per actual octave. And I can take that answer, store it in this answer variable, and I can multiply it by 13 to prove that this is equal to a 3-to-1 ratio. So I just take this and I divide it by 3-to-1, and I get almost exactly 1. Just because a little bit of numerical instability when it does all this math. So here's my 4 steps in 12-tone equal temperament, which is a major third, and here's my 6 steps in 19-tone equal temperament, which is also a major third. So I'm trying to figure out what's the distance between these two. And I can just do subtraction for that. And I can see that it's 0.21 steps in 12-tone equal temperament, which by just typing C and pressing enter, I can convert to cents. And so the major third in 12-tone equal temperament is 21 cents higher than the major third in 19-tone equal temperament. And you'll notice it came out in 12-tone equal temperament, which was the number of equal divisions of the octave of the first argument. So here I'm going to do some math, which is 6 in 19-tone equal temperament plus 2 in 31, just as a random example, and it's going to give me a result in 19-tone equal temperament. So if I reverse those arguments actually, and I put the 31-tone ET on the left, it'll give me a result in 31-tone. So one thing you might want to do is find out how well each equal temperament approximates your favorite just intervals. And so here's a just major third. And if I just want to find out the exact value, how many steps in 12-tone equal temperament this just major third is, I can just use 5 to 4 hash 12. And it's exactly 3.86 steps. And I can also check in 31-tone equal temperament how many steps that is. So almost exactly 10 steps is a just major third. And again, similarly, I can put this ratio as an argument to the ET function, and in this case, it'll convert it. Whereas before I was creating it from numbers, I'm actually using ET to convert a ratio here. And so here it converts it into 12-tone equal temperament. If I do the same thing and give it another argument, here it'll convert it into 31-tone equal temperament. I can actually do a similar thing with this Bowen-Pierce scale and say, okay, I want a major third in Bowen-Pierce, which is 13 divisions of 3-to-1. And so that's 2.64 steps in the Bowen-Pierce scale. And so let's say you're working with a certain equal division of the octave, and you want to find out how to best approximate a just interval. One way to do it is to calculate, so I want this interval, let's say 7 to 4, in some sort of equal temperament, let's say 31 tones per octave. And I want to actually round that, so I can round an ET value with the round function. I can actually round any value with the round function. And this will round it to the nearest integer step. So this will go to 25. Which means if I want to play this 7:4 ratio in 31 tone equal temperament, I just have to play 25 steps. I can do similar stuff for 12, for 19, whatever. Cool, so the only thing I didn't mention here is that we can also use a single character, just as before, to convert to ET. So let's say I have this ratio, and I can just use the hash. So if I put this into the console with nothing else, then it'll convert the last answer into an ET value. The other equal tempered data type in Zen is a number of cents. And so I can create cents by saying 14C, and I can also create cents by using the cents function and passing in something such as a number, creates 14 cents. And I can, of course, do other things like passing in a ratio to the cents function, which will convert it to cents. And whereas with ETs, they could be 19 tone or 31 tone, with cents, they're always exactly 1200 cents per octave. And just to show a little bit more of the notation, here's 5/4, and to convert it to cents, all I have to do is put a C after it, which means this value back here, convert it to cents. And I can do what's, 6 steps in 19 tone equal temperament, convert it to cents, 378. What's 4 steps in 12 tone equal temperament, convert it to cents, it's going to be 400. So this is useful when you have something like you want to find the difference between a just major third and this major third in 12 tone equal temperament, and you want the results in cents. So what that did is it took this value back here, and I happened to put it in parentheses because I want this operator to apply to all of it. It took that value back there, and it converted it to cents. I can do a similar thing with my other major third in 19 tone equal temperament, and whereas in 12 tone equal temperament we were 14 cents sharp, I can see that in 19 tone equal temperament we're going to be 7 cents flat of a just major third. That's about it for the equal tempered values. In the next video, I'm going to talk about frequencies.